Okay, today I just changed the title. I had nucleation kinetics, but I want to speak in general about precipitation kinetics. So, precipitation of a second phase inside a matrix phase. It's something which is technically of quite some importance. Because many alloys obtain their strengths and other properties by some precipitates, and you have to adjust the size of these precipitates in order to get the best hardness or conductivity or which other properties you are interested in. In the typical situation we consider, if you have a simple binary phase diagram, also B concentration, say it's a eutectic. There's an alpha phase and a beta phase. And experimentally what you typically do is you homogenize your material at a temperature where it is completely in the alpha phase. Yeah, so the B atoms, so think of aluminum copper, the copper atoms are homogeneously distributed. Then, very often for technical reasons you quench it down to room temperature and then you heat it to an annealing temperature. So you go down here and then you go up. Can one see this green? Yeah. You go up again to this temperature. So that's the homogenization temperature, and that's the aging or annealing temperature. What happens here? So we have the alloy at this concentration in the two-phase region. So this is, of course, alpha plus beta. And it starts to form clusters of beta with this concentration here, and the matrix depletes in B to this concentration here. So we have the following values here. We have this mu alpha 0 here. We have in equilibrium the alpha concentration here and the beta concentration. All these news are the B, new B beta, but I omit this. Yeah? This means that you form small clusters of the beta phase inside an alpha matrix. That's a typical phenomenon. In the classical description, the very simple description distinguishes three phases. I guess you all know. We have a nucleation phase. The very small clusters of this beta phase form. The next step, we have a growth phase. I'll explain in a moment what this means. And finally, we have the Ostwald ripening. So we can try to visualize these different phases here. No, not nice. So in the first step, we form very small clusters of beta. alpha matrix. No. But still, if you form this nuclei, you are close to this initial composition, so you still have a high supersaturation. Which means that you have lots of B atoms floating around in the matrix, looking for a place to go. And what they do is that they diffuse towards these nuclei which formed. So this first thing was step 1. Now we are in this growth phase where the B atoms from the supersaturation go to the existing clusters which formed in the first step. And then after a while, this supersaturation is nearly gone. So this was nucleation and growth. And that's this Ostwald ripening. What happens here? Now you have larger clusters, different size. And these smaller clusters, they will dissolve on the cost of the large ones. So I went briefly, just to remind you, I guess you all know, gives the laws which control these different phases here. In order to form such a nucleus of beta phase, you have to form a matrix precipitate interface. Oops. I don't know what this is. So the total energy to form such a cluster, on the one hand, it's the volume energy you gain if you form this beta phase. I call this delta GV. That's energy per volume times the volume of such a cluster. It has radius r. Plus now this interfacial energy. And from this you can derive an expression for the critical radius. There's roughly such a shape here, this curve. And here, once you reach this maximum, that's what we call the critical radius. If nuclei are smaller, they would dissolve again here, so they have no chance to survive. If they are larger, they can spontaneously grow. And this critical radius is given by perhaps I should define these terms here, gamma, alpha, beta. Specific interfacial energy. And delta GV is a gain in volume energy per volume. free energy to be more precise. One can make a very simple model or estimate for both quantities for this volume energy. One can estimate it from the phase diagram. These are all these quantities here. So nu beta minus nu alpha, that's the size of this miscibility gap. 1 minus nu alpha is 1 minus this here. Times kt logarithm. I should put a big roughly equal to, and for the interfacial energy, again one can make a very simple estimate in terms of broken bonds. So if you know nothing about your system, you can, using these terms, if you know the phase diagram, you can estimate the critical size of the precipitates here. So that's the first step.
But what is x alpha gz?
Which one?
Logarithm. The gamma alpha 0 is the overall composition, right?
I don't know. You mean these news here?
Those are compositions.
These are the compositions, yeah?
And this, in the logarithmic term, in the denominator,
So
what composition is that?
That's the equilibrium concentration of the alpha phase here. This one here.
Ah, I see.
So it's just this difference here, the supersaturation.
That is the supersaturation. And other alphas there, they are not equilibrium.
Yeah, I should omit this GG here. Then it's perhaps more clear. GG is German, means Gleichgewicht, equilibrium. So sorry for that. So that's the initial, the upper one is the initial composition here, and that's the final composition here. Okay, so this is pretty simple, and I suppose that many of you already know this. Then for the growth phase, again, we can make a very simple model. We look at the cross-section of a precipitate and the B concentration along this cross-section here. Here inside the precipitate, we have the nu beta. Outside the precipitate, that's some kind of assumption. Alpha and beta phase are in equilibrium. So we assume that here we have the nu alpha from the phase diagram. And only in some distance, we go towards the initial concentration. So here we have the precipitate. And here we have the matrix. And far from the matrix, we still have this initial concentration close to the matrix. The B atoms have migrated to the precipitate. That's why we have this depletion here around. Now what happens? Here you have a concentration gradient for B. So B atoms will migrate from the matrix towards this interface. So we have B diffusion. To the nucleus. And this, of course, leads to the growth of this nucleus. So after a while, this moves outward. And this interface is migrating. And for this case, one can write down the diffusion equation. We are not in one dimension, we are in 3 dimensions, or we assume that we are in 3 dimensions. So we have a radially symmetric, if everything is spherical. That's the radius, or the position. I put r here because I want now to go to spherical coordinates. Yeah. So this is the radius of the precipitate. We can write down the diffusion equation here for this spherical case. Yeah, I now use the concentration per volume. In other cases, normally I use the molar fraction. That's why I use a nu here. Nu is the molar fraction. C is so many atoms per cubic centimeter or so. But there's a very simple relation between both. Cb is nu b over omega. Omega is the atomic volume. And the diffusion equation for radially symmetric case is very simple. Sorry, it's not dt, dr square. For spherical symmetry. And this has a solution, stationary solution. Cb of r is C0 R0 is the starting size here, the critical size. And if you plug this in, you find a solution for this the size of the particles here. You can also write it for the average size. So this is the size at a time t. This is, oops, sorry, this should be 0. Size at 0, so that's the starting size here. That this obeys a very simple time law. Now I go back to this nu here. The important point is that the size, critical size or average size, that it goes, the square of it goes like t, or the size goes like square root of t. So very roughly speaking, the r goes like t power 1/2. often you find it as a T1/2 law. Yeah.
Why use star for the R? It is just R squared, right? R star is the critical size with which we started at t equal to 0.
Yeah, but the critical size now grows because the supersaturation goes down. And I mean, you can also write it for the average radius, but I think it's more obvious in principle to write it for the critical radius. I mean, when people do experiments, they study the average radius. Okay, so that's the second step. And I will show later that this distinction into these different phases is rather artificial. Huh? But here we assume that after a while, the supersaturation has vanished. Yeah? So all the extra B atoms have attached to some nuclei. So that's the third step. This is nearly as important. What is the basic idea of this Ostwald ripening? I think Ostwald developed these ideas for liquid droplets, so fog formation or so. I think it was beginning of 20th century or so. I'm not 100% sure. So what's this Ostwald ripening? If you have a small particle and a large particle, this one has a strong curvature. And this one has a comparably weak curvature. And one can look at it from different sides. From thermodynamics, we know that there is an extra term controlled by the curvature, 1 over r. So you get a higher concentration of B atoms around a strongly curved particle compared to here. It's known as vapor pressure of small droplets, Gibbs-Thomson effect. Oh, I wanted to look up whether this Thomson is written with a P or without a P. I think without a P. Yeah. Or around. Strongly curved. slightly increased. But one can look at, if you look from an atomistic point of view, one can understand it even simpler. If you think of an atomistic interface, yeah, for example, this atom here has only two neighbors. Yeah? If it is a very smooth interface, most of the atoms have, if it is a square lattice, have three neighbors. Yeah? So the binding of these surface or interface atoms here on a strongly curved interface is weaker as it would be on a weakly curved interface. This is a more perhaps intuitive way to understand this. As I mean, you can go through the thermodynamic derivation of the Gibbs-Thomson effect, which gives basically this result. So what happens now? This means that we have a higher concentration of B here than here, and this leads to a net flux of B atoms from the small nuclei to the big ones. And there is an amazing theory to describe this. I find it amazing. I don't know. Perhaps you have heard about it. In or by Lifshitz. Two Russians, Sliosov and Wagner. These two Russians wrote down this model in parallel to Wagner, and I think they published it at the same time. That's why we call this altogether the LSW theory. Wagner was a German, Karl Wagner, who made lots of contribution also to thermodynamics of solids or thermodynamics of metals, and also in corrosion you nearly every day come across this name of Karl Wagner. Wagner is a very common name in Germany, so I write down the first name. Lifshitz is the one, perhaps you know, the series on books in theoretical physics. It's 20 volume, or I forgot how many, huge collection, Landau and Lifshitz. And as Guru explained me, Lifshitz had to do all the writing, but Landau, Lev Landau also is a famous theoretical physicist with incredible contributions to many different fields, superconductivity and other things. Yeah, Sliosov, I don't know.
I haven't seen anything other than.
So maybe it was his PhD thesis, and then he went to reasonable things, and so these are these three LSW. And the strange thing or funny thing about this LSW theory is that for the size distribution of the nuclei or of the precipitates, you find very simple time and size laws. So if I call this f of r and t, oops, sorry. is given by a function phi. Yeah, principle I could skip one parameter, one step here. It's a bit twice the same. So it's given by a constant times an exponential minus tau. I explain in a moment what this tau is, but it's basically a scale time, yeah? Times the psi of r hat. R hat is a normalized size. To the average size. So I'm wondering, here's this psi of r, and if you are interested, I strongly recommend to go to these books of Landau and Lifshitz. There's I find incredible derivation of this law here for the psi, for the size distribution. Very tricky and easy to follow. This is a universal function here. This somewhat weird prefactors here. One over 1 minus 2r hat over 3. So this is exponential divided by 2 power 5/3 r hat minus 3 power 7/3 3/2 minus r hat power 11/3. But this is only true, you see, if you go beyond 3/2 for the scaled radius. So this is only for this here, and it's 0 for this. And I'm not 100% sure about my notes here. I think this I must check again. I think the tau is 9/4t. But I put a question mark here. I did not note it here. Basically, this means that we have this universal function for the size distribution, and we have just a shift of this size distribution with time. Or other way around, we can scale our size distribution by normalizing everything to the average size, and then typically normalizing this distribution to be to have an integral of 1 or so. I think I have examples here. I thought I have examples. Too bad I did not put them here into this presentation. It's a pity. We did it once for an experimental case. So let me think where I have it. Probably I have it here in one of my other lectures. Here I see an experimental situation with precipitates in aluminum lithium. They form nice spherical precipitates. Oh, these are the different phases here. Here's what I already said here. Here. And now this is the size distribution of this. They have a structure of aluminum 3 lithium, the well-known L12 structure, which we love. This is after 1 minute aging, I think at 150 Celsius or so. After 3 minutes, after 5 minutes, and here you see a second maximum arising. Yeah? Here, that's the nucleation phase, and now we get stable clusters here. It's after 10 minutes, 15 minutes, 20 minutes, and now we are slowly going into this coarsening regime. And here, this is after 6 hours. This is the experimental size distribution here, normalized by the average size. And here, this is just this graph of the LSW distribution. And there's no parameters, yeah, nothing fit. It's just normalized to this average size here.
LSW itself is derived assuming vanishing precipitate volume fraction and things.
Right, yeah. Yeah.
And no overlapping of diffusion fields and so on.
There's a lot of assumptions behind, and I will show examples. I mean, we are here in the computer simulation class, so there's I will show that for my Monte Carlo simulations, the coincidence is not that good. And to be honest, I don't know the reason. I mean, I tried to get into the field where this LSW should hold, but still there are some discrepancies.
Yeah, but I think
and
in simulations you also need much larger size, especially if you have periodic. I think that also affects the...
Perhaps, yeah. The assumption is that we have only diffusion via this Gibbs-Thompson effect, yeah, that there's no coagulation or so between clusters. And yeah, basically it means that you have pretty low concentration. Here it's not too low, nevertheless it's fine. And these precipitates, they have the L12 structure, so they have only 25% of lithium. So in principle it should not work, but it seems to work. Yeah. On the other side, this scaling behavior seems to be very stable against experimental deviations from the strict conditions. Yeah? At least part of this scaling behavior. I will show examples then. So, I think I can now switch back to this presentation. So what I did now is to put this in a Monte Carlo simulation. You see how precipitates form. I think this is, I forgot, I did not note it here, a few percent of B atoms. So here is not much happening. But if you look on a cross section, it's 10% here at 800 Kelvin. So I did 50 times 1 million Monte Carlo steps, and you see nicely the formation of these clusters. Here just visualize the central slice. This afternoon we will explain how to do it in Oviedo. This is for a longer time. Now it's 100 million steps in 50 snapshots. So we see here now that these clusters are already pretty large. Now we can try to evaluate this using the tools we have. So here you see the size distribution. And this is application of the Soshen-Koppelmann algorithm here. See, the particles get larger and larger. Here you have the subcritical nuclei, and here, this little bump here are the supercritical, the precipitates which grow. It's perhaps a bit misleading because still you have a pretty high number of dissolved atoms here. Yeah? Here at the bottom, oops, you see the index of time or of steps here. It's now 30 of 50 steps of these 1 billion Monte Carlo steps. And this is now at a lower cobalt concentration so that you have better distinction between these clusters. So the first thing you can do now is to plot this cluster size distribution. What's this here? That's the average size. So if you have the size distribution, you can determine the average size. And you can check these time laws I showed before, 1/2 and 1/3. So here you see just the size this average size is a function of Monte Carlo steps. I was too lazy to take this is all done with this residence time algorithm to take out the true Monte Carlo times. So this is for a short number of steps here, 100,000 or so, and this is for this large number. And the average size, you see, it increases. But now if you plot it on a, what is it? It's the average size is not the radius, but it's this number of atoms in the clusters. Yeah? So should be radius power 3. Yeah? So for this LSW behavior, you expect to find a linear time law. R power 3 would increase linearly with time. And for shorter times, you expect this t power 1/2 or t power 2/3. No, sorry. I think I made a mistake here. It's t power 3/2, not 2/3. So that's the size here plotted as a function of time, and you see that this t 1/3 law, or number of atoms in the cluster, average number proportional to time, is well met. Here, that's this line here would be this t to 3/2, which still is okay, I would say. So that far, it's okay. The very simple laws might be considered to be confirmed. Yeah. Now this was what I wanted or thought was next. Here I plotted the cumulative size distribution. So as I explained yesterday, instead of plotting the size histogram, as was shown in the other graphs here from the experimental work here in aluminum lithium, here I just add up the numbers. So many clusters have a size below 100 or so. Here you see 80,000 clusters. And that's for consecutive times. So for the first one, you see that still not all of the cobalt atoms are precipitated. This does not go to the limit value. So here we are still in the nucleation and growth phase. Here I would say still, but here we are now in this ripening phase. And now this is for much longer simulations here. It's for 10 to the 8 Monte Carlo steps. And watch here that I changed the scale here, so it's going up to 900. And for the longest time, yeah, you see that now the statistics becomes poor. Yeah, we just have not sufficient number of clusters of this size. And now we can do this scaling. So we normalize our size to the average size. And basically that's all. And you see, except for the very first one, these curves more or less, or the second one, these curves fall onto each other. And that's the same as I showed before for the real distribution. Yeah, I mean there you normalize to the average radius, and here for this integral size distribution you can do the same. So the scaling seems to be reasonably met. Here I even plotted once the real size distribution. And here you see something similar to what I showed in this experimental graph. Here you see the subcritical nuclei. I think the graph goes like this here in lines here. Yeah. And here we are in this coarsening regime. That's again another concentration, 3%, because at 1% the statistics is just too bad. Yeah?
Even in that, there is still a peak at the lower end.
Yes, and I mean, partly, of course, this peak comes from the fact that there is a finite solubility. Mm-hmm. So isolated cobalt atoms are counted as clusters of size 1. That's the first thing. But still, you have a certain supersaturation because of the Gibbs-Thompson effect. I don't know, I did not calculate how big it is. But here you see one difficulty I had. I showed this true LSW distribution, yeah, which is more or less asymmetric. Yeah? Maybe I should go back to it. Hope it's still open. No, it's not here. To reopen it again to remind you what this LSW function looks like. Oh, it's somewhere here. Okay, here we are. You see that the maximum is far to the right. Yeah? So here you have this slow increase and here you have a steep decrease. And this seems to be not the case here in this function. So this is the point. I don't know what the reason is, but apparently the conditions for this LSW are not well met here. Yeah, here's a fraction of precipitated atoms here, which approaches 1 after a long time. And here you see it, yeah, for 2 different concentrations, for 1% and for 3%. And of course you see that this precipitation process proceeds much faster at a higher concentration as it would do at a lower concentration. That's clear. I mean, if you have only 1%, the B atoms have to diffuse quite a long distance until they meet another one. For 3%, it's more probable. Okay. But now I wanted to show another way to look at this data. That's the so-called structure factor. What is a structure factor? Perhaps I should. Yes?
The simulations they are not kinetic Monte Carlo.
They are.
They are kinetic.
Yeah, I mean, I'm not very happy with these terms. I mean, I use a vacancy and I use a residence time algorithm. So I think that's
So
what.
the time scales.
Yeah, as I said, I was too lazy to take out the times. Perhaps this would change a bit. But I think after a while, the Monte Carlo time from the residence time gets more or less linear with a number of steps. Only in the beginning, where the number of B atoms, so the probability for a jump strongly changes because you have more configurations or different configurations. Then there are deviations. I should try it once, but okay. So that's another type of evaluation, is to calculate the structure factor. Basically, the structure factor is what you would get from a diffraction experiment. What does a diffraction experiment do? More or less, it Fourier transforms the arrangement of atoms. So you have atoms sitting here and here and here and here. So you have a function in 2D or in 3D. You can do a Fourier transform of this function. Yeah? We call it S of Q. Here what I want to consider is only the modulus of Q. So the Fourier transform psi of Q vector is just the sum over all positions of atoms here times exponential minus I Q R summed over all positions. And the sigma of R is whether it's 1 or 0 or -1 and +1. This would not change this structure factor except for the constant. Yeah. If at side R we have an A atom or a B atom. And then we have the amplitude, the intensity, I of Q, which is the psi of Q squared. And this S of Q, the structure factor, is a radial average over this I of Q. So you integrate all the intensities over shell. Yeah? Why are we interested in the structure factor? On the one hand, that's what you get out from a diffraction experiment, like neutron diffraction or X-ray diffraction, or so electron diffraction, perhaps. On the other side, the structure factor is a Fourier transform of the pair distribution function. what is a pair distribution function? It gives us the probability, if I start on one B atom, to find another B atom in a distance r. And this structure factor in the coarsening regime, in the Ostwald-Rappening regime, again obeys such nice scaling laws, which one could derive also from the LSW. So we need a Q1, which is the average first moment of the structure factor. If I write Q without an underscore and without this modulus bars here, I mean just this. So just to save some time. So that's the first moment of this structure factor. And now we can normalize everything to this first moment here. So that's the counterpart to the average size, yeah? And our S of Q we transform in an S hat of Q just by taking the third power. This we can do. And here you see this structure factor for this Monte Carlo simulations I did. You see that it is more and more forming a peak here at small q, which means large distances. Yeah? So q is, I don't know, are you familiar with reciprocal space and all these things? Everything is just 1 over. Yeah? So small q correspond to large distances. So this maximum moves to the left, which means our characteristic structures become larger. In principle here, from the slope, one could derive the average size or something. There's, okay. And now I did this scaling here, and you see for the first steps here, it does not nicely fit onto these scaled functions, but the further we go, the better it fits to the scaled structure factor.
The scale one, why does there is a change in slope?
So this pink one or this violet one?
All of them seem to have a change in slope after a while.
Yeah, this is, I think it's because it's for short. Oh, maybe. I thought it's because it's for pretty short times.
Well, okay, so that to that distance, no, larger q should be smaller distances, so diffusion should have happened.
What do you mean? You mean here this? Okay.
And you can see that also in the scale.
Mm. So this is this is probably the subfinite size effect of the box size. Yeah.
This time you will see
Yeah.
the other end.
Yeah, you're right. And it's always here at the same position.
Yeah.
Yeah, I do not care for that. So here you see it for longer times. Here before it was 10 to the 6 steps, now it's 10 to the 7. And if you do the scaling here, they all nicely fall on one common master curve. And I tried one other thing, and that's the point where I said I'm not 100% satisfied. I used these cumulative size distributions from before and put the LSW equation here in an integrated form onto this values here. And you see this does not fit nicely.
Is it because now you also have to scale the time? Till now
I
we have
don't
only been
think
scaling
so.
size, and for some time
Yeah,
those will be scaled to this, you think?
I think it's a matter. I can show in the next slide. So here, yeah, I just wrote down my confusion. In principle, all the conditions for LSW should be fulfilled, low concentration, long time, and so on, but it does not fit nicely. I tried something else. I just played a bit on the LSW function here. I shifted it a bit to the left, and I rescaled it more or less arbitrarily, and then you get a nice fit. So it might be a question of time scaling, might be also a question of spatial scaling, I don't know. So this is what I wanted to say about, I think, the next one. Okay. The next one is already something different, and I prepared some transparencies on this cluster dynamics as well. Either I continue or, yeah? So this is the classical picture of precipitation, distinguishing between these different phases, which is a bit arbitrary. This might be another reason why these things do not fit so well, or no, in principle not. Normally, under real conditions, of course, you don't have this distinction in particular between the nucleation phase and the growth phase. I mean, while nucleation still takes place, the growth already sets in. So this distinction, for sure, is rather artificial. And there's another way to describe this, which is called cluster dynamics. Which is perhaps even more powerful. So what is the idea behind this? And it is also a very fast and simple method. In this, in this very simple, I don't know whether one should call it a theory. We just consider average sizes, and we distinguish these three phases. In Monte Carlo, we just have the system running and look what comes out. But there's something in between, I would say, and that's this cluster dynamics. So we characterize the state of our system not by the position of the atoms, but we look how many clusters of a given size are present in this sample. So we have the cluster size distribution. Use the cluster size distribution. So this is what I showed on one of the slides here. Here, you have a certain size distribution. You have so many clusters of size 20, say, you have another number of 19, and so on. Yeah? So now what can happen? C of n number of clusters containing n atoms. So, such an histogram here. Perhaps something like this. How can the number of clusters of size n change? So what is dCn over dt? Can change if a cluster of size n minus 1 grows. Then we get one more of size n. So, and what's the probability? We have a growth rate alpha n minus 1. And of course, the probability is proportional to C n minus 1. Can also increase if a cluster of n plus 1 shrinks by one atom. So this is growth, and that's shrinkage. But the number of clusters of size n can also decrease. This is if a cluster of size n grows by 1, or if it loses an atom. So this adds a minus sign here. Minus, so here alpha is the growth. Alpha n Cn minus beta n Cn. And that's in principle a very simple evolution equation for such a size distribution. Yeah? You start with all monomers or so, with a whatever starting distribution, and then you let it run. Yeah? The only thing you need are expressions for this alpha and beta. How can we find this alpha and beta? So we have our cluster here containing n atoms. And it can grow if one free monomer, one single atom, adheres to this cluster. So I think okay, in my manuscript I used alpha and beta the other way around, so I have to be a bit careful. If I follow my manuscript, then I will confuse these two. But anyhow, so this is our alpha process. How can we give an expression for this? It's proportional to the diffusion coefficient. It is proportional to the surface of this cluster. And it's inversely proportional to the radius. And then it's proportional to the number of free monomers. Why do we have this 1 over r term here? That's the diffusion equation in 3 dimensions. Yeah? So you have a kind of inverted source solution here. It depends whether you consider a diffusion limited or an aggregation limited case. Yeah? Both is possible, but typically in metals we have this diffusion limited situation, so it takes time to transport B atoms to this cluster. And the aggregation to the existing cluster is very simple. I think if you have, for example, an oxidation process, it can be much more complicated to put this additional atom into this existing interface, and it's interface limited or aggregation limited or so. So this is for diffusion limited. Growth. So this is simple. Now we must say something about the shrinkage. C1 is a monomer concentration.
Around the precipitate, around this cluster.
We don't distinguish, we don't have a spatial structure.
Okay.
So we assume that the average concentration is everywhere the same. So there's no spatial structure at all. I mean, and magically, nevertheless, the Ostwald ripening comes out. So what can we say about the shrinkage probability? That an atom leaves an existing cluster here, that's our beta here. Here we use what we learned before, that we have this condition of detailed balance. The probability for a backward step times the number of systems in this state here, so number of clusters of size n. Has to be equal beta n Cn I have to be a bit careful with my alpha and beta here. I think it does not matter. So if we start with a cluster with n atoms, here beta n Cn, we have the probability for growth, alpha n minus 1, Cn minus 1. Or we could put it this way here, plus 1, So this is this condition of detailed balance. And I don't go through all steps here, but one can show that roughly this Cn is given by C1 power n exponential minus, I explain in a moment what the Fn is, Fn is we call the cluster free energy. A cluster with n atoms. In a moment I try to say a few more words about it. So from this now we can derive an expression for the beta. Equals our alpha n, 1 over the monomer concentration, and here this difference in cluster free energies. Here it's only 1, F1. Over kT. And here for the alpha n we can put the expression from above here, the C1 cancels out. And so this is d over omega pi a what is a yeah. Yeah, it's. I think I skipped one. Maybe I leave this out. I think I made a mistake here. But you see, it's very simple. If you have the alpha n to derive the beta n, as soon as you know this cluster free energy, what does it mean? Until here, when I use this term cluster, I always more or less had in mind a spherical cluster. But that's not necessarily the case. Yeah? If you think of a lattice here, occupied with B atoms, say a cluster like this. It's how many? 10 atoms. That's one possible arrangement. But instead you could also put the atoms on other positions. For example, you can put one here. So you have a huge number of configurations for such a cluster. And the cluster free, or the configurational sum of such a cluster is just the sum over all possible shapes this cluster can have times exponential minus the energy of such a cluster. This probably has a higher energy than this one. Maybe I'm wrong. But at least you can calculate the energy of such a cluster. And this you do in a Monte Carlo simulation. But under the condition, now you do a Monte Carlo simulation for a cluster of a given size, say 10 atoms, and you try to sample all the configurations, all the shapes it can have. Always respecting the constraint that the cluster stays a cluster. So don't consider a case where this atom moves here. Then you no longer have a 10 atomic cluster. Can be obtained simulation which samples not the whole crystal with 100,000 atoms or 1 million atoms, but a system with a pretty small number of atoms. Yeah? So that's very fast. So you do this sampling, and then you have to apply one of the methods we learned here. For example, this overlapping distribution method. That's what we used and where I learned this method. This overlapping distribution method, or I think also the other methods, you have to change the interaction model slowly. Here the change of the interaction is extremely simple. What you do is you change one B atom into an A atom. That is, you have another type of interaction between this atom and the rest of the atoms here, and vice versa. So you remove one atom, you add one atom here. This you do on a long chain of Monte Carlo steps, and then you get a good estimate of the cluster free energy, which we need here. I did this a long time ago, and my PhD student did it recently. So, and I want to show some results. Okay, I have it here on the slide. So what you obtain then is a f of n, the three energies of clusters of size n, as a function of the size. And then there is a very nice relation. What do you expect? And this goes a bit in the direction which I showed in the very beginning. Yeah? So the energy or the free energy of such a cluster depends on its volume and its surface. And if you want to do it even more precisely, you can add corner and edge contributions. Yeah? The volume is proportional to to the number of atoms in the cluster. So what you expect is f of n equals some these are other alphas and beta, the one I used before, sorry for that. So you have, or A and B perhaps, one term proportional to the size of the cluster, and the area, the interfacial area of this cluster to the matrix goes with power n to the 2/3. So what you expect here is such a relation here. For a two-dimensional cluster, this slightly changes. You keep this term proportional to n, and two-dimensional because in this thesis he studied the formation of these Guinea-Preston zones, which are platelets in this aluminum copper system. And then the interfacial area goes with size power 1/2. And then if you want to do it nicely, you add this logarithmic term. You could add it here as well, but it's of not very high importance. Here for this case, you can do the calculation of the configurational sum up to cluster size 3 or 4. I forgot, I once went through this exercise. For 3 it's simple. I mean, if you have next neighbor interactions, you have a linear and you have a triangular, and no, triangular not, you have this edge, no, an FCC. So that one can, but for 4, I think it's already becoming tedious. Here in 2D, I think you managed to calculate it on paper up to size 6 or so. And the rest of the points comes here from these Monte Carlo simulations. And this is fitted by this function here. That's the function which is plotted here with a dashed line. For different temperatures, for higher temperature, you expect to have stronger fluctuations of this cluster, so the free energy will slightly change. Here in this zoom, you see that they are slightly shifted against each other. Yeah, and these terms, A, B, and gamma, or C, the A corresponds to the volume energy of the precipitation process. B corresponds to the surface energy. Just by a normalization, you get the surface free energy. And the C, it's a correction factor. You see that these factors are temperature dependent here. You see continuous, since it's negative, it must be negative, of course, it's a gain in energy. Continuous decrease here, you see a, I don't know, not a very systematic behavior here for this interfacial energy and this gamma also. So that's what was obtained from Monte Carlo simulation. And now you can plug it into this cluster evolution equation, this set of equations dCn over t dt equals this and that. And then you get the evolution of the size distributions. So this is this here, I think the red one is the initial size distribution. Here the blue is for somewhat longer time, green longer time, orange even longer time. These curves are results from the cluster distribution, CD called here. And the points are result from Monte Carlo. You see that for short times it nicely fits. For longer times it does not fit, but becomes a constant here. And there's a very, very simple reason for this. There's just one cluster remaining in the simulation box, and you can't make any statistics. Here, that's this cumulative size distribution, and here you see the average size. Always solid line, the result from the cluster distribution, the points here from the Monte Carlo. Here the precipitated volume fraction, which approaches 1, And here's a number of clusters per volume. And it's interesting to look at this curve here. Here, this is the nucleation phase. Not very much happens. Yeah? And then it abruptly goes up. So you form many small nuclei. And then when this coarsening phase sets in, the number goes down again. And here in this extreme case, you end up just with one huge cluster. So this is nice. And as I said, this was done for more or less, it's not for a 2D system, but for a system containing two-dimensional or platelet precipitates. One should not mix up these two. Here you see this concentration dependence here for two different sets of concentration here, 0.5 and 2%. And here these quantities here for different temperatures, 423, no comparison for two different temperatures, these quantities, sorry, and so on. So this all fits nicely. And here, this I took from old work I made some long time ago, similar for 3D. Here again, more or less used the data for copper cobalt, 10%. So this size distribution looks similar to what we had before. In the beginning, you have this high amount of subcritical precipitates, and then you form here's the critical nucleus size, and then you form these stable precipitates. And here I applied again the scaling law. So I divided the cluster number here, cluster density by the maximum, so that they are all normalized. And I normalized the sizes here, which are here the number of atoms, to the mean size, and you see how nicely they all fit on one master curve. Except here, of course, during the process, the number of monomers goes down, but here in this coarsening regime, everything falls on one curve. So again, you find more or less the LSW results, or at least any kind of scaling behavior, whatever you do. Yeah? And that's some strange experience. I mean, in the example of the Monte Carlo simulation I showed, the LSW behavior did not fit so well. But in experiments, even if the conditions of the LSW theory are not fulfilled, at least you find this T⁻⁰ law, except when you have elastic strain. I think Guru mentioned this case of the nickel-based superalloys, where the growth of the precipitates is strongly slowed down due to elastic effects. Yeah? But if you have other, I don't know, deviations in size, if the particles are not spherical or so, nevertheless, you always find this T⁻⁰ behavior. So this LSW is very stable against experiments, I would say. Okay, I think I stop here. Thank you for your attention.
At least some of you use ParaView regularly, at least from our group at least. No? I don't know if you use ParaView. Do you use ParaView often? Matplotlib, okay. How about others? Is there anybody else who is using ParaView? Okay. So you can think of this as a very short tutorial introduction just to start ParaView. Okay. It's not complete, but I will show you there are lots of resources. So like everything else, you have to load ParaView, and if you are using a Linux machine, that is fairly easy. You can use, for example, in Ubuntu apt-get and get ParaView. And this is the interface that shows up. The first thing that we want to do is to load data, and for loading you have to write it in a format called VTK, and lamps and sparks allow you to dump data in VTK format, and so it makes life easy. So, this much at least I did show. So, we open the file, and for that we need so you can choose the file that you want. I think day 5 we did some icing. Icing is here. Okay, day 6. So, you can open the VTK file and it asks which reader you should use, and we opened that day and we saw that it is XML based. So, we put the XML reader, and now you have loaded the data. Do not know if you can see here at this left corner there is an eye symbol. You can make it visible or invisible by clicking on it, and I say apply, and like I showed the other day, nothing happens because the representation currently it is in some uniform grid as outlined, but we know that this data consists of the icing, the spins. So, you want to say that you show it as a surface, for example, or surface with the edge, for example, or as volume, for example. So, you have to choose one of these. So, let us say that we want to choose it as surface, and you choose spin. Now, it colors according to spin, okay, and you can change the color scheme by changing the color map here. You can set the color map, there are several. For example, you can put the X-ray one, okay, and if you run now, this is the way to run. So, you can run now, this is how it looks, okay, and you can change this to whatever you want, and there are also other ways. For example, okay, you can change it to why is it not changing color for me? Okay, so it does. So, you can change the colors and you can run, and upstairs that what you see here, okay. So, this is another one. Of course, you can rotate whichever way you want, and if I do some random stuff, then there are these here, set view direction to minus z, set view direction to plus z. If I do, it will come back. And this is a 2D simulation. So, if I set my view direction to x and y, you will see that it is just some line like this. In 3D, of course, you can set it to whichever direction you want, and you can do this. You can rotate, there is plus 90 and minus 90 rotation, that is possible, and you can put a small indicator as to what are the directions. So, the star one, the point 1 is the direction outside of the screen, and that is the x and that is y. So, you can, and if you rotate this, you will see that it rotates, okay. So, whichever orientation you have this, you will be able to easily see by having this small marker to tell you. It is basically the indication of the axis, okay. Now, most of the times we also want to add the time in the plot. For doing that, you just need to add an annotation, and annotation is annotate time filter. Now, again annotate time filter, you have to make it visible. Now, if you make it visible and run, pay attention to this corner, you will see that it starts putting the time, okay. you can not only add time like this, you can also add some title that you want to give, for example, and for that you use annotate and sorry, it is not highlighted because there is no annotation for the time itself. So, you have to go back to the image and then you annotate a text. Why is it not giving me? You can add a text. Okay. Now, the text that I add here, for example, is that icing simulation animation from Sparks example, right. I can apply, I can make it visible. You will see this is also common. There are many different places where the same thing can be done. Okay. For example, you can click on the eye or you can say apply, they do both the. Now, you see that they are overlapping. So, you do not want this annotation to show up there. You can change its position by going and deciding where it should display. Okay, you can display wherever you want. Okay. You can also add a box which gives the color scheme. There is a box. Okay, why did it show? So, if you do not want, you can of course delete. I should have a, okay. So, you can also annotate by putting a logo, which is some. So, you can choose where you want. I had a logo here in this directory. Where is the logo? Yeah. Okay, I am not able to locate. Let me see. No. Okay. Yesterday I could add. Okay, so let me see in filters, in annotation, sorry. It's not there. Okay, I'll locate the way to add. You can also add a logo to the image. I'll try to locate and show you. So, you can put the color legend. Okay. So, this is the color legend and you can add and you can edit it just by moving it. Okay. There is also a way to change its length, for example. Maybe your advisor says no, this should be in line with this, and you can do all this just by doing this. Okay. And then the other important thing that you want to do is to make a movie out of it. Okay. So, that you can do, you can save screenshot, you can save the images, you can export a specific scene and you can save animation. So, for animation let me use this test.avi as the file and I say OK, and it says already exists, do you want to overwrite? I say yes, I say OK. Then it will go with the simulation, it will generate this, and I have given a frame 1, that is why it is slow. You can also make frame 5, 10, etc. So, you will get a right. So, now let us go back and run this video that we have made. Right. On the top you see time and bottom it is written what it is, and you see the axis marked and you see the color scheme which tells you which color correspond to what value of spin. There is only 1 and 2, okay. So, the rest of the color is just interpolation using the color triangle, but you can see that you can make the video out of it. Now, sometimes what we are interested in, which also often students in our group use, and I also strongly recommend that people use, is that of course, you can do this cutting, splicing, etc. So, there are things here you can see, right. This one is for clipping, this one is for slicing, and this one is for some threshold, and you can extract some region and so on. So, these are done, but one of the things that we find often very useful is to plot over line, and you can see that line is starting here. I do not know if it is very clear here, and it is going there, and this plot over line you can apply, you will get. You can also change. So, you might want to just see this, for example, and you can get it here, and you can minimize or you can maximize these views. Okay. So, you can also bring this up and take the image back, that is also possible. Now, whatever you did with this image, you can also do with the figure. Here, for example, you can add a time annotation. You can annotate time, for example. Okay. If you apply, then you will get the time coming on top for you, and you can change the position of time, right, like you did last time. So, you can bring time here, for example. So, this you can do. Similarly, you can do other things. Let me see if I am successful with the logo one more time. It does not allow me to choose. Where is the? Okay, that is where it is. Sorry. Okay. Now, it still is not visible because I have to apply. Once I apply, it should show up. Where did it show? What happened? Okay. Let me try this again. sources, annotation, logo, texture, ITB. Yes, you can see in the bottom the logo has come. Okay, very good. So, I can go to this plot over line, I can make this visible, annotate time visible. Let me go back and see, hopefully it is there. So, I close that. Okay. Sorry. You can see the line. Okay. Instead of doing this camera thing, I closed it. Okay. Okay. So, you can also get this plot over line, and you can change the plot over line. Okay, let me redo it again. What happened to me? Spin, I have representation surface, solid color spin. Okay, very good. So, plot over line and yeah. My mouse is not behaving properly. Okay, so I am going to exit and I am going to redo. So, you can load, it will remember the recent files. So, I can load, I can apply, and I can make it surface, I can make it spin, I can change the color map, let me make it linear green. Okay. What happened? I do not know why the spins are like this. I find this problem sometimes, if it is connected to other display etc. My mouse does not behave properly. Spin. Okay. So, we were at this point where we were trying to draw a overline, filter, there is plot overline. So, there are many places where you can plot overline. Last time I showed you on this thing, and you can also plot overline here. Okay. Now, you apply, you get the overline. what you can do is you can bring this up, you can now make a movie. So, I am going to make another movie, save animation, that is the test2.avi. We say yes, and I am going to change the frame rate. So, you get another movie. Now, this time this is not the movie of the microstructure, but this is the movie of the composition profile. Okay. So, you can draw this line to anywhere and you can bring this up, you can plot this, make a movie out of it, take a shot and so on. So, I think it also allows you to keep the current state, whatever you have loaded and whatever you have done saved. So, you can go back to that if you want. Let us go back. Okay. So, plot over line, you can annotate time, you can annotate text, you can add orientation axis, you can orient along x, y, z I showed you, you can clip, slice etc. So, that is something that you have seen, for example, here, right. You can apply, okay, or you can, right. Why is it not showing? Yeah, so it clipped the this thing, you think? Here? No, I don't think it clipped here. Right? Oh, yeah, my VTK. It's where I am. It doesn't.
That is visible. My VTK,
Huh.
make it unvisible so that it's
Oh, the clip will be seen. Oh, okay. So it's showing both. Right. Slice type plane, that is okay. You want me to slice in the other direction here, okay. But this is not what I wanted. Okay, let me remove this, delete, let me delete this also, let me delete this also. Now I have to view this. Okay. Now let me try to plane origin is 250, 250.5. Okay, x normal apply. No, is that this one I have to, it's not showing. Camera normal, reset to camera normal, it's not doing. Okay, so now it sliced, at least now it sliced previously. Okay, so you can, I thought I had. Yes. Okay. So, it was already in slice, so that is why I was not able to slice. You can make a surface and then you can slice it, and you can do this other operation, and you can slice whichever direction you want, x, y, z. So, you should have a surface for it to slice. I was already in slice, and that is why I was not getting. Okay, so, you can clip, slice, you can animate, you can modify color bar, you can add logo, and you can use palettes. Is there anything else that you use, Subhash or Sushil? Contour? Okay, so that is in the rendering type, is it? Okay, let me delete this. Contour is not here. Okay, you have to add a filter or source. How do you?
The second icon in the last, before the click.
Here? This is surface.
No, the toolbar just below.
Below? Here?
Second one from the beginning.
This one?
That is supposed to highlight.
Yeah, no, that will highlight. Okay, it will highlight because at this point probably it doesn't have anything. Which one? Yeah, maybe because of the data. It will highlight this, yeah. So, okay, so fine. So, here is before this clip is where the contour is, if you want to. So, it also does not do any of this histogram etc. because of this data. Okay. This VTK has, I mean, in sparse you can write only one value per site, that is generally the spin. So, there is not much that it can do in terms of that. That is why some of this are not. This is plot overline, that works anyway. Yeah. Okay, so I will stop here. I think we have taken enough time. But this is a good visualization tool. We also use it for other codes that we write. Mohan, for example, is writing code for this project that we have called microsim, which is an open source phase field code, and you can visualize the data from there using, it is written in VTK. Among other things, you can also use ParaView to visualize that data. Okay, any questions? So, in that case I will stop here. Afternoon we will come back. There is some more thermodynamics that is still pending that I have to do, which we will do. This is related to interfaces, and the classical definition is Gibbsian, and I will show that there are other definitions that are possible, and also a careful definition of what is an interface becomes important when you are looking at solid melt interfaces. And how do we do, what is the basis, and how do we carry out simulations? You will see that pretty much some 2-3 steps we have already done, but there are 2 more steps which we do today and in the next time. Okay. And that also forms the basis for our other formulation for getting the anisotropy of interface properties. So, that also depends on understanding the some of the thermodynamic fundamentals of interfaces, which is what we will do in the afternoon, and afternoon Ferdi will do similar thing for Ovito. And in Ovito, for atomistic simulations you can do a little bit more than what ParaView can do. So, he will show you all those things. Okay. So, I am going to stop here, and we will meet in the afternoon at 3 today.